So our intuition says that if we're looking at a line, a basis for a line is one vector. If we're looking at a plane, a basis for a plane must be two vectors. What this theorem does is it confirms that intuition. So suppose we have two different bases for either Rn or a subspace of Rn, so a vector space, okay? The vectors in the first basis is v1, v2, all the way to vt, so there's t vectors. The basis in the second, or the vectors in the second basis, are w1, w2, all the way to ws. So this second basis has s vectors, how many it has. The claim here, the thing that we are going to prove is that s equals t. That is, you might have two different bases, but if they're bases for the same vector space, then they were going to have the same number of vectors in them. Okay? So we're going to prove this actually by contradiction. In this proof technique, you prove or you assume the assumption. Okay, so we're assuming we have two bases, B and C, of a vector space. All right, but then you assume that this isn't true. So we're going to assume that S is not equal to T. And then we show that exploring this, some nonsense happens, so that assuming both of those at the same time is impossible. You can't have both two different bases for a vector space and different numbers of vectors in the vector space. Okay? All right. So suppose S and T are different. That means one of them must be bigger. Okay? Now, it really doesn't matter which one we say is bigger, so we're just going to say the second one is bigger, right? We just decided to name one basis B and name one basis C. But if we wanted to, if this was actually the bigger basis, then we could just swap them. We could just rename them. Okay? So that's this line here, without loss of generality. That's what it's saying. You know, we're assuming that one is bigger than the other, but it really doesn't matter which one it is because we could just rename them. Without loss of generality, assume that S is bigger than T, which means basis C has more vectors in it than basis B. Okay? Now, basis B spans V. That's one of the definitions of a basis. So every vector in basis C can be written as a linear combination of the elements of the vectors in B, right? Remember, since B spans the vector space, every vector in the vector space can be written as a linear combination of the spanning set of vectors. Okay, that includes these vectors. These vectors are in the vector space, and so they can be written as a linear combination of these vectors. Okay, so W1 or W2 or W3 could be written as a linear combination of these vectors, or generally Wi. So here we're taking I to be anything between 1 and S. Okay, so we're just saying every one of these W's can be written as a linear combination of vectors V that form basis B. Okay? Now, what we are going to do is we're going to look at the homogeneous equation with vectors W, which are the spanning set of basis C. They're the basis vectors in basis C, our second basis. Okay? So what we're going to do, we now have an expression of every vector W in terms of V. So we're going to plug that in for every vector here. Okay? So all we're doing is we're saying, oh yeah, okay, this expression on the left-hand side of the equation is right here. But then for every W, we can rewrite it as a linear combination of the vectors in V. So we have B1, and then instead of W1, we have a linear combination of the vectors V. Okay? Plus B2, and then instead of W2, we have a linear combination of the vectors V, which forms our basis B, right? And I could keep on doing this for every W. Okay? Now what we do is we rearrange. So I notice that if I distribute here and I distribute here, that I'll have B1A11V1 and B2A12V1 and so on. So I'm going to just combine all those V1 terms. So I have B1A11 and B2A12 and all the way until I get to the very last one, BSA1S. And all of those are multiplied by V1. So I have V1 at the end there that I factored out. And then I could do the same thing again for V2. B1A21V2, B1A21V2, B2A22V2, B2A22V2, and so on. Okay, so I'm just combining like terms and then factoring out the common vector. All right? Now remember, this expression is equal to 0. And so that means this big nasty looking expression is also equal to 0. Notice we've expressed it as a linear combination of the vectors V. Okay? We have a constant times a vector plus the constant times a vector plus a constant times a vector. That's a linear combination of vectors V. And it equals 0. What do we know about linearly independent vectors? We know, by the way, that the V's are linearly independent because, by assumption, B, with all those vectors V, is a basis. And remember, a basis is linearly independent. That's one of the properties of a basis. Okay? Because the V's are linearly independent, the only way that this linear combination is equal to 0 is if all the coefficients of the linear equation are equal to 0, right? The trivial solution is the only solution to this linear combination equation, which means this coefficient has to be 0, and this coefficient has to be 0, and the coefficient in front of VT has to be 0, because all those V's are linearly independent. And that's what this is saying. All those coefficients have to be 0. Okay? Here, notice they are using J. They're just saying all values of J between 1 and T. Okay? So when J is equal to 1, that's the coefficient of V1. When J equals 2, right, that's coefficient of V2. So this is going to be true for all those J. Okay? So if we put all those equations together, it gives us a system of equations. All right? The coefficients of the system are the A's. So they go in the coefficient matrix. The variables of the system are the B's. Okay? And we know it's equal to 0, the 0 vector. Okay? Now, let's think about the rank of this system. Remember what we know about S and T. By the way, look at this. How many rows do we have? A11, A21, all the way to AT1. We have T rows. And how many columns? We have A11, A12, all the way to A1S, so we must have S columns. Okay, and remember our original assumption. We assumed that S is bigger than T. That means we have more columns, so S is bigger than T, so we have more columns than we have rows. Okay, so the max rank of the matrix is equal to T, right? Because remember, the rank is equal to the number of non-zero rows. Every row has to have a leading entry. Every non-zero row has to have a leading entry in our coefficient matrix. And so if we get this thing in reduced row echelon form, the most leading entries we can have would be one for each row. But since we have more columns than rows, that means we can't have a leading entry for each column. And that means we would have, if our rank is less than the number of columns, that means we have free variables. And infinitely many solutions. Okay? And so this shows that this equation here also has a non-trivial solution. Remember, the whole way we got this system here, is we said we started with this and then we plugged in, right? Remember the b's here are the coefficients here. If we have infinitely many solutions here, the b's are the solution to this system also. Those coefficients of b. If we have infinitely many solutions, that means these can't all be zero. Or rather, that wouldn't be the only solution because we have infinitely many solutions. So there would be some way to choose the b's so that they aren't all zero, since we have infinitely many solutions, right? Which means these are the same b's. We could use those same b's that aren't all zero to solve this equation. But that would mean that the vectors in W aren't linearly independent. Remember, in order for this to be linearly independent, you could only have the trivial solution of this where all the b's are zero. Okay? So that means by what we've looked at, these can't be linearly independent. They must be linearly dependent. And there's our contradiction. Remember, I said this was a proof by contradiction. We assume, the assumption here, that we have two bases. Okay? And we did. We assumed that, which means, though, that this set of vectors B are linearly independent, set of vectors in C are linearly independent. And then we assumed that this wasn't true. So we assumed S was not T. And from there, we were able to come to something that's nonsense. We said, oh, but these vectors are linearly dependent. And that contradicts our other assumption at the beginning, that the vectors form a basis for the subspace, because a basis is linearly independent. That contradiction means that this statement and this statement together are impossible. They cannot both be true at the same time. So if this statement is true, then this statement must be false. If S is not equal to T, then that means that S actually does equal T. Okay? And that's the conclusion. We conclude that S does equal T. All right? All right. This was a complicated proof. Hopefully you kind of understood a little bit of what was going on. Here's the punchline, though. If you have two bases for the same subspace, they will always have the same number of vectors. Two different bases for the same subspace will always have the same number of vectors. So a plane, a basis for a plane, will always consist of two vectors. A basis for a line, no matter which vector you use, a basis for a line will always have one vector. Okay? And what this does is it allows us to talk about how many vectors will be in a basis without having to think about a particular basis, because all the bases for a given subspace will have the same number of vectors in them. And so this gives us a definition. Let V be a subspace of Rn. The dimension of V is the number m of elements in any basis of V. And as we just proved, that definition is consistent because any basis of a vector space will have the same number of vectors in that basis. Okay, any two different bases. So we write that the dimension of V is equal to m. So quick example. Take the standard basis of Rn. Okay, how many vectors are here? Well, E1, E2, E3, all the way to En. We know that forms a basis. It's the standard basis of Rn. So the dimension of Rn is equal to n. Any basis for Rn, whether it's a standard basis or some other basis, must have n vectors in them, n linearly independent vectors that span the space.